So till now, we have seen two types of modeling. Okay, there is one generative modeling and there is one discriminative. In generative modeling, we have seen naive Bayes algorithm, then GDS and GNVs. Okay, in discriminative model, we have seen KNN, decision trees, logistic regression, perceptron, and SVM, which we saw just now. Right now, we will see the assemble classifier or meta classifier. We can say. The idea behind these are very simple. Choose a weak learner or classifier. Okay, choose a weak classifier or learner, and then convert it into a strong learner. Okay, this is our goal. And this weak learner, why we selecting weak learner? Because weak learner is better than any random learner we will select. Okay, that is, rather than selecting any random learner, we will select a weak learner. Okay, now there is two things. Okay, why with weak learners? Okay, so there will be two scenarios. First is either it will overfit or it will underfit, right? So let's say we selected any algorithm which not perform that much. Okay, so it is underfitting, but there is some algorithm which is like exceptionally performing well. That is overfitting. Okay, so overfit means it fits the noise in the data. Whatever the noise present in the data, it also fits that. Whereas if we talk about underfitting, underfitting means it's missing the structural thinking, okay, that it is a noise. It means that uh, where there is some noise or something, it will miss the structure of the underlying data. Okay, let's visualize this. So this is our normal expectation, okay, from the algorithm. Let's say I can say strong algorithm, correct? Now, how underfitting look like? Okay, so let's say these are our data points. Okay, and we selected any random learner which give me a line like this. So let's say we selected a linear classifier. Okay, let's say or regression. Okay, so here you can see these are the errors, like uh, errors. Okay, now let us suppose we took a new data point here. Okay, just like in original or say good classifier, on this data point it classifies correctly. Okay, what underfitting happens? Okay, so if we got this data point, or let's say this data point or this data point, okay, so we will see there is very large difference. Like for these all data points lie in these particular region, okay, it will consider that as a noise, or it will basically underfit the data. Okay, so what we do, let's say we have a complex learner. Okay, so for these data points, let's say it exactly fits that data. Let's say 100% correctness on our uh, training data. So it will form like this, like it is going through all the data. Let's say again the same point we took, which we had in previous underfitting case. Okay, for this data, you can see the prediction is so much. Okay, there is so much variance. So when there is a overfitting, it gives high variance. Okay, it gives high variance. While there is underfitting, it gives high bias. Okay, and we have already studied about bias variance trade-offs, right? That is, error is equals to bias plus variance. So we need a algorithm or learner which will try to balance both of these. Like, we want to minimize the error, for which we have to balance these bias and variance. Okay, so neither we want an underfit, okay, so that our bias goes up, or neither we want nor we want overfitting, which means high variance. Okay, we want a balance so that our error can be minimal, right? So we will have a algorithm known as bagging, okay, which is also known as bootstrap aggregation. Okay, so what bagging does? Let's say we have data sets D1, D2, up to DM. These all are data sets. Okay, different data sets where each DI is n points. Okay, now for each point, let's say we have some HI, that is our model. Okay, where HI takes RD and outputs +1 or -1. Okay, so for each data point, let's say we have a model. Okay, that is H1, H2, up to HM for M data sets. Now, what bagging will do, it will aggregate all these classes. Okay, so from all these H, we get a H star of X, that is nothing but equals to sine of 1 by m of summation of I equals to 1 to m of all HIs. Okay, where sine of z will be plus if z is greater than equals to 0, and will be minus if z is less than equals to 0. Okay, so what we did, we had m data sets, we calculated HIs, and then we aggregated. So we bagged up, and from bagging all the HIs, all the learners, we pick a average, which will perform better. Now there is something. Let's understand the process of bootstrapping. As we said, now bootstrap aggregation. So what is this bootstrap? Okay, so bootstrapping is basically sampling with replacement. Okay, so as we are, let's say we had some data set, and from that data set we created m data sets, and we generated m learners as well. Okay, so what we will try to do, we will try to do sample the data set with replacements. Okay, so let's say we had data, let's say x1, x2, x3, x4, x5. Okay, so we will create a bag. Okay, let's say we have a bag. Now what we did, we just start picking up, we just start sampling data with replacement. Okay, so let's say we first pick the x3, put it into the bag. Okay, then x4, put it into the bag, then x5, put it into the bag. Let's say again we picked up x3, so again put some bag. Again, let's say we got x5, put it in the bag. Now this bag is our d1 data set. Similarly, we again sample. Okay, that will be a D2 data set. Similarly, we will get DM data sets. Okay, so we will get M bags with M number of data sets. Okay, and all these data sets are sampled with replacement, that is bootstrap. Okay, now run algorithm on this DI and find a H star X. Okay, now how we will find H star X? For every DI, right, we will get a H. And now, after getting all these H, we will do this aggregation, right? And we will get a H star of X. I hope this is clear to you. Let's understand it pictorially, basically what we are doing. So we had a data set with n points, we sampled, that is, we did the bootstrapping. Okay, we bootstrapped and got a m data set which is sampled with replacement. Now from each di we will get a wl, right? From each one weak learner we will get from each d, right? Now what we did, we did this aggregation, right? So there is two steps involved in this bagging. One is bootstrapping and another one is aggregation. Okay, yes. So the thing is, why we are doing bagging basically. So bagging will do what bagging will do? Bagging will reduce the variance. Okay, bagging will reduce the variance and the probability that a data point xj belongs to a dataset dj, right? Someone from these data points. The probability that a point belongs to that dataset is basically this much: 1 minus 1 minus 1 by n raised to power m n. Okay, that is approximately 1 minus 1 by E, which is approximately 67% for a large n. Okay, if our n is large, then this quantity is nothing but approximately 67%. Okay, so the bagging is an algorithm, okay, which reduces the variance. Okay, so here, like, bagging will reduce the variance. Okay, so there is one popular algorithm we have, that is the random forest algorithm. Okay, I hope you understand the bagging. Bagging consists of two steps: bootstrapping and aggregation. Okay, so random forest is a algorithm which is based on this bagging. So what it does, it bags decision trees. Okay, typically overfit trees. Okay, random forest will first bags the decision tree. Okay, means that it samples dm trees. Okay, after that it do a feature bagging. Okay, feature bagging is a modified form of bagging, where what it does, it picks a subset of feature to consider splitting. Okay, what it does, it picks the subset of feature. Okay, it bags the features for every node of tree, and the number of features will be root under d. I don't, we don't know from where it comes. It's basically uh, from some calculations. Okay, but the number is, it does root d of features. Okay, it consider root d features and do the bagging. So that is called feature bagging, and then aggregates to get the out. Okay, so this is how this is a random forest algorithm works. Now we also have boosting. Okay, and in boosting we will learn about AdaBoost. Okay, so here uh, idea is seen that we will start with some weak learner and will reach to a strong learner. Okay, but the thing is, the catch is here is, it can be underfit classifier as well. That is, the weak learners can be a underfit classifier as well. At any classifier it will consider in boosting. Okay, and it is easy to get a weak classifier. Okay, so underfit classifiers are there. So let's say I can start with a linear classifier, right? It is easy to get, and as I see, so shown you in picture, right? This is a weak learner and we can easily get it, right, by regression or something. So starting with a weak learner, we will reach to strong learner. It allows underfit classifier as well, and it is basically easy to find okay, such a weak classifier. And there is a term which we use for these type of classifier, that weak classifier we are talking about, that is decision stumps. So decision stumps is nothing but a level 1 or level 2 classifiers. Okay, that is one level or two level. Let's say two nodes, two height disjunktly. Okay, so such type of learner we can take, and then we will reach to strong learner. Okay, the algorithm is okay. So focus here, you will get it easily. That we have input S, okay, where we have x1, y1 up to x and y, where xi belongs to Rd and y I of course belongs to plus 1 minus 1. What we do, that we start with a distribution. Okay, initially we start with distribution, let's say uniform distribution, okay, which is also known as weights here. In this context, we will say weights or uniform distribution. Okay. So first, what we did, we initialized a distribution or a weight, that is a uniform distribution, which is 1 by n. Now, for t equals to 1 to t, okay. First, we initialize the distribution. Now, we will change this distribution accordingly. Okay. So for t equals to 1 to t, okay, there is ht, which is nothing but which will take input as s and that distribution. Okay, s is this and the distribution, okay, to a weak learner to get a ht. Okay, so basically ht nothing but takes input of these two and gives us a ht. Okay, rd, which takes rd and put gives us plus 1 or minus 1. Okay, where s is the data set and dt is the weight. So for t equals to 1 to t, it takes the data set and the distribution as well to give us a ht. Okay, how it does this? So basically, after d of t plus 1 times of I is nothing but equals to dt of I into e of some alpha times t. If this h of t xi is not equals to yi, okay, and dt of I into e raised to power minus alpha t if h of t of xi is equals to y. Okay, so what it does basically, as I said, first we initialize the distribution, okay, and then we change the distribution accordingly, like iterative. Okay, so we inputted here to get a ht. Okay, now with help of that ht, basically either it gives a plus 1 or minus 1. So if ht is equals to the predicted output, then we will multiply with alpha t. Okay, that is we are changing the distribution. Okay, if there is the actual output is not equals to the output. Now, if it is equals to that output, then we subtracts e of minus alpha t basically. Okay. So again, we did a change. Okay. So ultimately, when it get changed, okay, and this is a distribution. Okay, this is a distribution, and we are changing the distribution. So as we increase, here we increased, here we decreased the distribution or the probability, because weights, right? It is nothing but a probability. Okay. So as we change the weights, the sum of both these, okay, will not be equals to 1. The probabilities will change, right? The weight will change, then it will not sum up to 1. So as we increasing or decreasing the weights, the sum will not be 1 anymore. So what we will do, we will normalize it. So the update that is happened is basically this step. This is intermediate step which I shown you, that there is some increase in data distribution, or there is some decrease in distribution. That is ultimately I'm saying that there is some change in distribution. Okay, and the update is basically d of t plus 1, that is the new distribution, is basically d of t plus 1 of I upon summation of sum of all d of t plus 1 of g. That is all the d's, whatever we got from initial to final. Okay, we will sum all those. Okay, and this is basically the current change upon my total distribution weights, right? That is nothing but we are basically normalizing it. Okay, so let's say it's like our probability 0.2, so we will do basically 0.2 upon 0.2 plus 0.8. Let's say the 0.8 is let's say previous uh, weight. Okay, so we are basically normalizing it. Okay, so that our sum is always equals to 1. So this is basically the algorithm. Okay, we initializing the distribution, then we are basically updating this distribution accordingly, so we will reach to a good learn, right? At last we have t different learners, right? So each time we are updating, we are getting this. For each iteration we will get some ht, for which our distribution get changed accordingly, right? After t iteration we will get some t hs, that is t models, right? Now we have to combine it, we have to aggregate it. So how we will combine this? So we will do this the following. H star of x is basically sum over t equals to 1 to t sum alpha t times ht of x. Okay, that is our aggregated weight. Okay, this is our aggregated weight, aggregated model. That is the model weight for strong classifier. Okay, the idea was to start from weak classifier and reach to strong classifier. So this is our strong classifier, where this alpha t is basically nothing but natural log of 1 minus error of ht upon error of ht. Okay, so this is basically alpha t, which came here and here also. So this is the alpha t. Okay, now there is a rule that if t is greater than 1 upon 2 gamma square log natural log of 2n. Okay, if our t, that is the iterative time, how much time we iterate. Okay, if this t is greater than this quantity, then there will be zero training error. Okay, that is our data does not do any training error. Okay, and this alpha, this gamma actually, sorry, this gamma is basically shows that how good is my weak learner than any random. Okay, so this gamma is the representation of how good is my weak learner than any random. Okay, now how does the boosting performs on the data, test data? Basically we did this for trained data, right? We did this for trained data, we got the condition that yes, this happened, then we will get a zero training error. Then how it will perform in test data? So let's say we have this. Okay, and this red line is basically what is the training error, okay, which our algorithm was making. So as the t increases, our training error will reduce and it will go to 0, right? As I said, it if this goes greater than equals to t, if t is greater than equals to this, then our training error will be 0. So as we increase RT, it will reduce the error, and after certain t, that is t star, it will go to 0. Correct? Now, how it will perform on test data? So when we get test data, it will perform like this. So it will reduce the error, and then it will go clean. But it won't go to 0. Why? Because it is a test data, right? So test data can have any type of input, right? There will be some bias outliers. So we know that it can't whatever our algorithm learned on some test data, it won't every time give a accurate result, right? It will not give accurate result each time. It will make some mistakes. So that's why the error will never be 0, right? So this is how boosting perform on test data, that the error will goes down, right? Now there is some disadvantage of boosting, that it can't run in parallel as it is an iterative algorithm. So we seen here that we are iteratively doing it, right? We are iteratively doing this boosting, that is AdaBoost algorithm. So as this is iterative, so we have to wait for the previous result to come before going to next result, right? While here it was like in this boot bagging thing, we had this m data points or m data sets, and we can parallelly perform these operations to get the double, right? So we can parallelly perform these much of the step to get, and then there will be one last step, that is aggregation. But here we can't do that. So this is the disadvantage of uh, boosting. Okay, but in real scenarios, boosting perform better. Just is it's with it we can't perform it parallel. Okay, so this is basically bagging and boosting. I hope you understood it very well. Okay, so we will see you in next video. Till now,